you had a great day so far. I'm Donato, I'm from Zircuit, and today I'm going to explain what Zircuit is, why it exists, how it has been built in infrastructure, etc., etc. And I'm also going to explain how to build an application on Zircuit. So, why Zircuit? We need to scale Ethereum. So the reason the existence of Zircuit is the same as every other rollup. We want to make transactions cheaper, we want to make them faster. We want to do this because the user base is growing. We saw it with the raising prices of the last times. We want to start developing new kinds of applications, kind of like high throughput applications and similar to that. And we also have other scopes like banking the unbanked and the mass adoption. Okay, what's the problem? We have the scalability, the blockchain trilemma, the famous trilemma introduced by Vitalik. It says that you can't have more than two of these three things, and Ethereum is one of those systems that is very decentralized, it's very secure, not as scalable as we would like it to be. Other examples are Bitcoin and other blockchains as well. So what has been done so far to try to solve this problem? A few scalability solutions were proposed. One is state channels. State channels were actually good. You can send as many transactions as you want for free. But they had this problem that the amount of users that they could work on was not unlimited. You had a fixed amount of users that could use the state channels. Side chains also were able to scale Ethereum. The problem is that they do not inherit any security from the layer 1, from Ethereum itself. So we don't have the same security assumptions as Ethereum, which is what we would like to keep on a scalability solution for it. The third, the Plasma, is able actually to inherit security from Ethereum and validate state transition on chain. The problem is that the data availability is not available there. And that's how we got to rollups. Rollups are the system that satisfy the requirements that were understood from trying to develop all of the scalability solutions I showed you before. We want the system to be open to everyone. We want it to be secured by L1. We want it to have data availability guarantees that are the same as the layer 1 data availability guarantees. And of course, we want it to be scalable. Otherwise, we would just use Ethereum. So, what is a rollup? A rollup is a blockchain on which anyone can transact. It is secured by L1. The state transition is secured by L1, as well as the data availability. And anyone can transact, deposit, withdraw, etc., etc. So how does a rollup look like? This is the architecture of a general rollup. It is inspired by the one of the optimistic stack, however, the optimism stack. However, you can see that it is quite common for many other kinds of infrastructure. The network of a rollup looks very, very similar to the Ethereum network. It's made of nodes that include an execution node, which is get, the same we have on layer 1, modified a little bit to welcome all the needs of the specific layer 2 you're developing. And we have a consensus node that says which one is the right story of the right fork of the chain, and there's also other duties that we're not going to get into right now. It also needs an L1 node because, of course, it needs to know the state of the L1 chain and behave accordingly. One of the nodes of a rollup is called sequencer. The sequencer is the part of the system that decides which transactions get in the chain. It decides the order of the transactions, and it's also the system responsible to update the layer 1 with data, the transaction data of the layer 2, and also the state transitions. So it has, in addition to all of the components that are already listed, also a batcher, which is the system that updates the layer 1 with new transaction, using it can use different kinds of data availability systems. The original one was to use cold data, now we have blobs. In Zircuit we're using blobs. And the proposer. The proposer is the service that updates the layer 1 with new states, the new output routes of the chain. And then we have smart contracts. The most famous and probably one of the most important is the bridge. It's the one responsible for withdrawing, for depositing, and doing other kinds of operations. We have the state transitions manager. It's a contract that stores states, all the states that are in the different blocks of the chain. And depending on the kind of roll-up, we have a verifier or a challenge contract. So roll-ups, nowadays they are divided in two kinds. We have optimistic roll-ups and the zero-knowledge roll-ups. What these two kinds of systems try to solve is the task of communicating to the layer 1 that a state transition is valid or not. So the way it works is that okay. So let's imagine how do you understand this, that if a state is valid or not? You can literally just spin up a node by yourself. You can run all of the transactions and check if the actual state is the state transition is correct or not by seeing your local state and comparing it with the state that you see on chain. So we can either ask Ethereum to do that, but then it wouldn't make any sense because we would not scale it anymore. Instead, we want to use Ethereum for data availability, but we do not want to use it for execution. Optimistic rollups have this thing called challenge game that allows the participants of this system to challenge a state that has been proposed on chain, demonstrating in some way that that state cannot be valid. And an optimistic rollup assumes that if after a week a state has not been successfully challenged, it can be trusted, it can be used as final, and it can be used to allow withdrawals from users. On the other hand, zero-knowledge rollups use this new cryptographic tool called zero-knowledge proofs to check that a state transition is valid, and they do it by actually verifying the state transition. The way they do it is by using zero-knowledge proofs that allow you to check that an output of a program is correct given the program and the input of this specific program, without having to actually run the code of this program, but by running a much smaller set of operations. In this way, you can check that an output is correct without running the Ethereum transactions, the layer 2 transactions. Okay. And now I'd like to present Zircuit. Zircuit is a zero-knowledge rollup. It is strongly focused on security. And when I say that it's strongly focused on security, I mean that not only we care a lot about taking care of the security of the infrastructure of the system itself, of Zircuit, but we also put a strong emphasis on securing users and protocols that deploy on Zircuit. We have a security stack that includes a secure native bridge. You do not need to trust third-party bridges. You have a native communication between layer 1 and layer 2 so that you can withdraw and you can deposit at any time totally independently and in a trustless manner. In addition to this, and this is what distinguishes us from other rollups, we do real-time monitoring of transactions. We do simulation of these transactions. We understand if the transaction is a potential a potential transaction that could lead to an hack. And if that's the case, we quarantine the transaction. Other than that, we also have active support for users and developers to review any sort of thing regarding the security of their setup. But let's get to the monitoring part that I just mentioned. We introduced this new feature, this new tool called sequencer level security. How does it work? It's an oracle connected to the sequencer. It's literally an AI-powered server that the sequencer queries every time it receives a transaction from users, from other nodes of the network. And before the transaction is included in the mempool, it is analyzed by this AI-powered tool. And if the analysis leads to a flag that says potential hack, we quarantine the transaction, we don't allow the inclusion in the chain, and we keep the chain secure from this kind of hacks. This is something that can protect users not only from smart contract hacks, but also from scams or rug pulls and other kinds of exploits. It does not affect at all the user experience of users. It's a totally transparent tool. You can use Zircuit the same way you would use any other EVM-based blockchain, or the same way you would use, for example, Ethereum. And yeah, it's something that can benefit anyone, developers, institutions, and anyone that would like to have a bit more peace of mind. So, how has been Zircuit built? We are a fork of the Optimism stack. So we decided to join the Optimism stack with the zero-knowledge provers. So instead of using the challenge game, instead of using the proposers of Optimism, we have our own system that takes care of proposing, proving, and verifying transactions. Our ZK EVM is built on Halo 2. It's a system that is trusted also by the PSC teams, Code and Tycho. And we also have developed some tooling to automatically check Halo 2 circuit constraints. Okay, let's wrap it up. How is the Zircuit architecture made? We have a sequencer that takes transactions from users or from other nodes. The sequencer is connected to the AI-powered analysis. The blocks that are generated by the sequencer are fed to the provers that generate the zero-knowledge proofs. They generate an artifact that is then given to the verifier contract to check that the state transition is correct. These blocks are free from hack transactions because we already filtered them through the sequencer level security. The provers have the unique optimizations that I exposed before, and the proofs that are generated by the provers are given to the L1 by the state proposer. I'd like to put strong emphasis on the security through research element of the diagram. We really are strongly focused on security, and everything we do is always based on a security first mindset. So, how do you build your own application on Zircuit? You're going to go through the tools, the network parameters, the smart contracts that you need to use to actually get your application up and running on Zircuit. How do you do it? Have you ever built on Ethereum? It's just the same thing. You just need to get some ETH on Ethereum on your wallet, and you can already start transacting on it using MetaMask, Foundry, or that. Deploying smart contracts and using Ethereum the same way you would, it's using Zircuit the same way you would use Ethereum. Just one difference, we have 2 seconds of block time. So, where do you get started? Zircuit.com has everything you need. The website exposes not only Zircuit and how it works, but it has also useful links to our Explorer, to our bridge, the documentation, and many other things. We have a testnet. The testnet currently is up and running. It also has an Explorer and a bridge. that you can access just by adding testnet in the middle. This is an example of what you will get from the documentation. You can find the network parameters that you need to connect your wallet and your developing tools. We have a set of contracts that are the ones I mentioned before for interacting with the chain. And you can use any tool you already use on Ethereum. These are the ones that I use, so that's what I listed. But if you have any other thing that you're used to use on Ethereum, it will surely work on Zircuit as well. Okay, let's try to use the standard bridge all together. Let me get out of here. So I made this project called, I didn't give it a name, but I made this project in VS Code. I literally installed hardhat.m and then just the ERC20. I needed an ERC20 from OpenZeppelin, so I just took it. I just installed OpenZeppelin contracts. I've set it up to connect to Sepolia and to Zircuit testnet. I have an M file that contains my Sepolia URL and my private key, and we can just get right into it. I have made a bunch of scripts to show how to perform a deposit. So, as I was showing before, the standard bridge has a receive function. Of course, it has a bridge it and a bridge ERC20 function. The beautiful thing of this bridge is that you don't need to call the bridge it function. If you just send it, it will bridge them right away. So I'm using this wallet. This is not the right network. Just a second. Sepolia. Okay, I have 10 ETH on Sepolia. And I'm gonna run this script. As you can see, I'm just selecting the signer. I am crafting a transaction that is nothing more than specifying the destination address and an amount of ETH that I want to send. And that's it. Then I send it and I wait for it to be mined and log the receipt. At the moment I have 10 ETH on Sepolia and I have 20 ETH on Zircuit. Let's run it. So I first specify the network. I want to run it on Sepolia, and I want to run this one. All right, let's go. Taking a while, but what happens here once the transaction is actually mined? The smart contract will emit an event. The event will be picked by the sequencer, and included, it will be analyzed by the sequencer level security to check if it represents an hack or not. And after that, the transaction data will be added to a transaction included in the layer 2 itself. And there you go. So now we should have 21 ETH here as soon as it updates. There you go. And we should have 1 ETH less on Sepolia. Did I have 11? I don't remember. I mean, the credit happened, so. Oh, there you go. 9 ETH on Sepolia. You can also bridge ERC20. I actually made an example of how to bridge ERC22. And here it is. I have, again, the same setup. I'm getting a signer. I have the bridge smart contract. You can get this smart contract just by checking out the documentation. You go on documentation. Check out the testnet part of the documentation, contract addresses. And once you get here, you can get a list of all of the contracts of the chain. Among these, there is the L1 standard bridge. And this is the address you need to interact with it. You can even check out the implementation by seeing it on Etherscan. And from Etherscan itself, you can even get the ABI that you might need to interact with it. For example, on Hardhat, you need to send a transaction using one of the functions of the contract. So the function we are going to use now is this one, is the one I just called. And we are going to use the bridge ERC20 function. It takes as input the local token, the remote token. I will explain this concept soon. And an amount and other optional parameters. So I'm connecting to that. I am doing an approval transaction and an actual bridging transaction. There you go. And this transaction goes through the same process I explained before of the sequencer using the sequencer level security to analyze the correctness and non-fraudulent nature of the transaction. So we got the approval transaction that went in, and also the actual transaction. I actually forgot to show you the token that I was bridging, but I just bridged USDT. I just basically sent 10 USDT. We can just do it again. So right now we have 46. And we should get 56 at the end of the process. Okay. And there you go. We get the 56 USDT. The same thing can be done the other way around. If you want to withdraw funds from Zircuit, in the same page that I showed before, you can see the contract addresses on L2. Among these, there is the L2 standard bridge, which is this pre-deployed address, this address of a pre-deployed contract. And yeah, you can interact with it the same way you would interact with the standard bridge on the L1. In this case, I don't need to do an approval because this contract is considered a trusted contract. But I'm inverting the two addresses in the code to the bridge ERC20 function. And we can run this thing again. There you go. I'm using this address, 0x13. And we are going to see later where we need this. In this case, the transaction didn't go to the L1, it went directly to the get instance of the L2. Now that the transaction went through, we can go here on the, this is the testnet explorer. And if you go here under, let me zoom out to show it a little bit better. Under blockchain, you can check out the latest L2, L1 transactions. And here you can see the transaction that they just submitted. It is waiting to be proved because the state has not reached L1 yet, because the provers right now are running all the operations needed to generate the proof that is later sent to the layer 1. But I already made some transactions before. These are mine, this and this. You need to prove the transaction to be able to show to the bridge that the transaction is an actually valid transaction. You need to prove that it belongs to the state of the chain at a certain point in the story, in the history of the chain. It's taking a while today, but usually it's much faster. Oh, here it is. There you go. Do anything? Oh, proving successful. So if I refresh this thing, we should see. There you go. Now it's in finalization period. It's a period after which you are actually able to finalize the transaction. I already have a transaction that I proved some time ago, and now it's ready to finalize, and I can actually click here. Right now I have on Sepolia 140 USDT. If I execute this transaction, I should get back my funds and see that number increase. These are two transactions that are sent on L1, the proving and the finalizing transaction. And there you go. Now we should have 141 USDT. Nice. Okay. So this was a demo on how to use the additional features of Zircuit that allow you to interact with the native bridge. We just saw how to interact with the standard bridge, but we have also other kinds of smart contracts. The most relevant are the standard bridge that I just showed you. Then we have other kinds of contracts. One of them is the mintable ERC20 or 721. Using these contracts, you can create your own representation of any ERC20 or ERC721 on either at the L1 chain or the L2 chain. In this way, you can bridge any token that you prefer. And then we have other contracts such as the custom messenger and the optimism portal. These are much lower level, but these allow you to develop your own bridging logic. You can use any kind of contract that you want to develop that doesn't necessarily implement the ERC20 standard or the ERC721 standard. So that was how to build an application in Zircuit. We do not do only technical stuff, we also have an amazing ecosystem team. That should be a 2. There we go. We have a Build to Earn program. It's a program that will get you. You can get actually financial and also technical support to build your own application. So I strongly invite you to apply if you intend to build something new on top of Zircuit. We have a liquidity hub. You can stake on Zircuit and earn different kinds of rewards, such as staking yield, top protocol tokens, points, and future airdrops. These are our launching partners. The liquidity hub allows you to stake assets that are both liquidity restaking tokens as well as staking liquid staking tokens. We have more than 26 assets. You don't need to lock up anything. You can deposit and withdraw from the staking whenever you want. And now we even have some new BTC-based assets. And that was it. We are Zircuit. We are trying to scale Ethereum using AI to check if the transactions are secure. Again, we have a virtual program, and you can check out our staking app. And we are a team of giga brains. We do a strong research on security, as I mentioned before. We have a lot of authored papers, such as bridge hacks based papers and other papers that explore topics regarding rollups and security in general, such as formal methods. We also received 3 Ethereum Foundation grants for researching on rollups. And these are our backers. If you want to have the link. And that's it. Thank you very much. And if you have any questions, these are our handles. We have later a talk by Giuseppe. Sorry, just a second, wrong window. We have a talk on November 15 at Zircuit by Giuseppe. He's one of our cryptographers. You can check out the way the polynomial commitment schemes are used for zero-knowledge proof systems, if you're more interested in our zero-knowledge part. And yeah, thank you again. I can't see my... here, there you go.
Hello. Yeah, thanks.
Thank you.
Yeah, that was a big round of applause.